that again, just to make sure. We still good. We got it. Good. All right. So the other thing that I'm going to be doing is recording lectures. You guys read it? So, got a webcam. It has a microphone. It's on this. I checked it out. It looks decent-ish. So, it's not the best, but I'm just going to be recording it, throwing it up on my YouTube channel. There's going to be a playlist called AP Lectures. The titles are going to be the dates. So, if you missed today, it's 10:20. Look for 10:20. You'll get today's lecture. So, if you are in Pride, if you're in football, if you're in track, you guys are in track, right?
Oh, we're switching over here soon, yeah.
Okay. So yeah, it's one of those things. Like if you're in an extracurricular and you miss it, you got a YouTube. I know you guys have YouTube on your phones because you watch it all the time in this class. So, I get it. So, if you go through, if you miss something, you can do that. Additionally, if you just didn't get a topic, there's one. It may not be the best, but it's here. So there's that. All good. Any other announcements? I talked about the lab. We talked about that. The next exam is going to be in. There'll be this week, next week, week after that, in 4 weeks. So you got about a full month before the next exam. We got a fair bit of topics coming in. Okay, so this one may be a bit bigger. So we're going to be talking about intermolecular forces. We talked about intramolecular forces. Remember way back in chapter 1, we talked about the electrons and the protons and the electronegativity and all that. What were the 2 things that I said you got to remember about that? It all relates back down to 2 things. The size of the magnet and distance is the distance between the things, right? So energy levels, that's how big, how far they are apart. You have the distance. You also have the how big the magnet is. Essentially, that's how big of a different charge you have, how isolated those charges are, and how close they are together. Okay. Now think about that in terms of bonds, right? You guys remember ionic bonds? Let me draw an ionic bond for you. Done. Here's the thing. Where are all the electrons here?
That's a good question.
This side, right? So if I are these guys sharing electrons at all? Are there any in the middle? No. So we have in this case 2 charged particles. One has all the electrons. So what do you think that means? That means that these guys magnets. The charge difference is pretty big, right? Difference in charge, pretty big. You guys remember ionic compounds? They exist in that lattice structure?
Yes.
Tightly packed together.
Right.
What's the distance between them? Pretty close. So if they're pretty close together, big magnet, what do you think the strength of this bond is going to be? Pretty high, right? So we have this pretty high thing. High strength bond. Now we also have, this is a covalent molecule, hydrogen fluoride, HF. Fluorine is pretty electronegative, right? So where are the electrons in this one? Over there towards the fluorine, right? So if it's over there towards the fluorine, then this is going to be a polar molecule, right? What is the charge difference between the 2 atoms? There's going to be a charge difference, right? Over here in the fluorine, it's going to be kind of negative. Over here on the hydrogen, it's going to be slightly positive, right? So you do have a little bit of a charge difference, okay? Distance, so it's not quite as tight as an ionic bond, but they're pretty close together, okay? So which one's going to be stronger? Ionic's going to be short. Let's keeping on. Nonpolar bonds. Where's the electrons?
In the middle.
Everywhere, right? Evenly distributed all across. What's the charge difference? Yeah, there is none, right? Nonpolar things, not a whole lot of charge difference there. So, that means that based on strength, this is the weakest one, right? We all good so far? Okay. Metallic is a little bit weird. I'm going to skip over that. Okay. All right. Just to keep things in order, I'm going to write over here ionic, polar, nonpolar. Now, all of these so far have been forces in a molecule, right? What we call intramolecular forces, not intermolecular forces. All good? Now we're going to be talking about intermolecular forces. So let's say we had a hydrogen fluoride and hydrogen fluoride. Like I said here, this has a slight negative charge on the fluorine, right? This hydrogen has a slight positive charge. It's positive and a negative. What's going to happen? It's going to attract. Put little traction lines in there. So if that happens, what's the charge difference of these guys? I mean, there's a difference in the charge, yeah? What's the distance between the molecules? It's going to be pretty far apart, right? You see how we can add those two concepts still can be used throughout all this? Okay. So, always go back and think about those things. All right. We're going to be talking about those intermolecular forces and kind of expand out this list. I'll say this. All of these guys are bonds. The stuff we're talking about, there's one thing called a hydrogen bond. That's a misnomer. It's not a bond. Like many things in life, this is a spectrum, and then we kind of drew a line and said, these are bonds, these are intermolecular forces. Okay? They do the same thing, it's just some are stronger, and we kind of drew a line saying, okay, yeah, these are bonds, these are just forces. Okay. Okay, so whenever we go about this, I'm going to talk about 4 different intermolecular forces today, and I want you to think about how does this relate in terms of solubility, and how does it relate in terms of melting point or boiling point. We kind of did this already with these guys, right? Yeah? So let's kind of think about that. How do these intermolecular forces play into these things? Yeah? All right. So, it's going to be that. This is an older slide set. I'm adding a 4th. Okay, so dipole forces. If you guys remember, a dipole is if you have a polar thing, right? Let's actually draw in the valence electrons to these guys. Where are all the electrons going to go? That way, right? So, the fact that all the electrons are over here, making this negative and this positive, this situation is a dipole. Think about it like this. Di means 2. Pole, like polar, it has a positive pole and a negative pole. The 2 poles, dipole. Okay? Okay. So we're going to talk about dipole forces, and then we're going to talk about hydrogen bonding. Again, not an actual bond, that's a history thing, London dispersion forces, and then ion dipole forces. Now, remember what I said about chemistry, we're either the best namers or the worst namers. What do you think is involved in a dipole-dipole force?
Those dipoles.
Those dipoles, exactly. What do you think is involved in hydrogen bonding? Hydrogen, and then other things. We'll talk about it in a little bit. Ion dipole forces? An ion and a dipole. Done. London dispersion forces, this is where, like, there was a period in time when scientists got really vain and they named everything after themselves. It was a dumb time. We don't talk about it often. Actually, we talk about it all the freaking time. It's the Great Enlightenment. But who do you think discovered London dispersion forces?
Some dude named Jonathan.
Some guy named London. Now, there's that. So these are going to be what we're going to be talking about. We're going to put these guys on this list. Okay. We all good so far? Dipole-dipole forces. So, basically we have two dipoles. Makes sense. And when you have a dipole, like in this case we have, this thing is acetone. Okay? This is what acetone looks like. Now, acetone has this carbon and oxygen double bond. Which one is more electronegative? Carbon or oxygen? Carbon or oxygen? Oxygen. I'm going to give you guys a big ol' hint. If you see nitrogen, oxygen, fluorine, those three boys, F-O-N, FON,
Oh yeah, fun.
that is going to be your electronegative atoms. Okay? They are going to be the hungry electron grubbing atoms that just suck up as many electrons as they can. F-O-N. So, oxygen, that's going to be a negative charge because it's sucking up all the electrons. This carbon is going to be a positive charge. So, you have that. Now, if you have another acetone, this oxygen's negative charge, this one's positive charge. What's going to happen? Positive, negative. If you have a positive charge and a negative charge, what are they going to do? You're going to attract to one another. You're going to have that dipole-dipole interaction, right? So, acetone. How many people have played around with acetone? Or just worked with it or done anything with acetone? Right? You kind of. What about nail polish remover? Yeah. Okay, so nail polish remover, acetone. Okay. So, it's acetone with a little, some other stuff, that way it doesn't kill your hands, mess with your skin. So, but acetone, whenever you see it, just at room temperature, what is it? Solid, liquid, or gas? It's a liquid. If you spill it, does it evaporate pretty quickly? It evaporates pretty quickly, right? It has a boiling point, so it'll turn into a gas at 56 C. When does water turn into a gas? 100 C. So that means that water has less or more forces in it than acetone does. Let me talk about something else. Let's talk about propane. Okay? Let me draw propane for you. Here's propane. But how similar is it to acetone, though? What's the difference between acetone and propane? That oxygen, that double bonded oxygen in the central carbon, right? So, that double bonded oxygen, what did it actually do? Is there a dipole here? No. Carbon and hydrogen are both about the same electronegativity. No dipole. Dipole. We added a dipole. What is propane normally? Like if you just had a container, it's a gas. When so I think it's like negative 30 C is when you have to get propane below negative 30 C for it to turn into a liquid, right? So that one thing different, this oxygen, this one thing different went from negative 30 to 56 C. All because of this dipole-dipole interaction. We added this one interaction, and now these molecules are sticking closer together. They're harder to break apart, right? So dipole-dipole interactions, they're pretty good. So dipole, they're pretty strong. I want to put them kind of in the middle. Not as strong as an actual bond, but pretty strong. You guys see what I mean? All good? More interactions. The melting point or the boiling point goes up. Okay. Now, hydrogen bonds. Now, chemistry is 5,000 years old. Okay, literally 5,000 years old. We've changed things. Back in the day, we thought that this was an actual bond. Like there were actual sharing of electrons. They're not. There's no actual sharing of electrons, but it's just super strong. Now let's think about why it's super strong. Let's talk about what it is at first. So a hydrogen bond, first off, you need a hydrogen. Okay? This hydrogen needs to be bonded to a super electronegative atom. FON. Okay? One of those guys. So if it's bound to oxygen, that means this oxygen is really electronegative. How many electrons does hydrogen have to begin with? One. So if that super electronegative oxygen takes that electron away from hydrogen, what happens? What's hydrogen left with? Zero. What is hydrogen then? Just a proton. Positive charge by itself. Okay? So you have a positive charge thing out here. So I'm going to say this. It's not a full positive charge. Not a full positive charge. But I'm going to say that it's a high slight positive charge. Kind of like upper middle class, you know? So this is an upper slight positive charge. All good? So, in a normal dipole, it would just be a slight charge. This is a little bit, have more of an oomph to it. So it's a, upper slight positive charge. Likewise, over here, this is an upper negative charge for the oxygen, right? And if we get into this situation, over here on this water, this is again upper slight negative charge and an upper slight positive charge. Compared to a dipole, a normal dipole, what's this interaction going to be like? Remember, if I increase the charge, the charge difference, it's going to be stronger, right? Same distance away, increase the magnet, stronger charge, right? In fact, if I'm going to put it here, I'd put it right there, okay? In between nonpolar and dipole-dipole. Okay, and this is why, so again, just to clarify, to make sure we know this, you need to have three things. Hydrogen bound to electronegative atom, FON, and then that's going to interact with an electronegative atom, which is bound to another hydrogen. Okay? You need those three things to go into play. All good?
One atoms.
So what?
One atoms.
One atoms?
One atoms.
Fun atoms, yeah. The way I remember it, because I'm old, you guys know the song Girls Just Want to Have Fun? Well, hydrogens just want to have fun. Yeah. I'm old. So there's that. It's very, very strong. This is one reason why water has a boiling point of 100 degrees Celsius, right? Acetone, that's, 56, right? Not only do you just have one like this, though, I can have another oxygen, or another water molecule here. Bam, got that. I can have a water molecule up here. Bam, did that. And not only that, this guy can be interacting with one hydrogen. Excuse me. But let me ask you this. This negative charge here, how does it relate to this positive charge? If I were to say this positive charge is 0.25, what is this negative charge? Positive charge, positive charge. So it's double it, right? 0.5, yeah. So it's whatever this slight charge is here, positive charge here, this negative charge is twice that amount. There's two slight charges there. Make sense? Okay. So that means, could this happen? Where this oxygen is interacting with two hydrogens? Yeah. 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 So, I mean, look at this one water molecule can be interacting with 4 different other water molecules. So not only are these really strong interactions, not only are these guys close together, you have your two things that you need to take care of, the distance and the charge difference, right? The other thing you need to worry about now is how many interactions can you fit on this thing. Okay? So we're adding one more thing onto the mix. So think about how many things we can get. It's not that bad. All right. So far, so good? You guys good with hydrogen bonds?
Yeah.
What if this? So you have water and NH3. Will these guys hydrogen bond together?
Yeah.
Yeah.
Those hydrogen groups.
Yep. So this hydrogen will interact with that nitrogen. This hydrogen will interact with the oxygen. You all good? Yeah. The more interactions you got, the stronger it is. But then again, how many things are there? Well, we'll get into it. This is one reason why water has such a high melting point, but this is also one reason why it has the surface tension it does. So if you take that penny you're spinning around and drip water onto it, how much water can you fit on it?
The surface area of the penny.
More than that. Think about it. What does water do whenever you drop it onto things? Makes a little bubble, doesn't it? It beads up, right? You can actually put, I think my record was 60 drops. Yeah. You can put a crap ton of water onto a penny. Okay, just by just being gentle. You know? But that surface area, that surface tension, is really high. Why is that surface tension so high? Those hydrogen bonds, right? how can we lower that surface tension? How does one lower the surface tension of water?
It says
Do what?
heat it up, but I don't think that's right.
Heat it up, that's one way you can break those intermolecular forces, sure. That's one way if you want to take these intermolecular forces and turn it into a gas, you break it. Sure. Let me give you, putting something in it. I'm going for a specific thing. So yes, you're going to be putting something in it. But what is one thing you can put in it?
Electricity.
No. What are some of the other things that we, what are some things you can put into water? Salt. Salt. So, let's go through it. I'm going to put salt in here. There's a positive charge. There's a negative charge, right?
Okay.
So now, this oxygen got a choice. It got options. Okay? It could go and do this, and it's a really strong bond, right? But if it just so happens to be close to this sodium, this positive charge, it's going to break that bond and interact with the sodium. So what do you call this with an ion and a dipole? Ion dipole forces. Okay? Ion dipole forces. They're pretty weak. They're not great. But you throw salt in there, some of those hydrogen bonds are going to turn to ion dipole forces. And if that's the case, we're taking something that has a lot of really strong bonds, or not bonds, sorry, strong intermolecular forces, and switching it over to weaker intermolecular forces. So what does that do up in the big boy world that we live in? How many drops of water can I fit on that penny? Less.
So does that mean that hydrogens can, like multiple, can interact with that negative ion?
Yeah. Well, we get to that next slide.
Oh, okay.
Okay. Are we all good? So let's think about solubility. Why is it that water is such an amazing solvent? Or I'm sorry, not next slide. Let's talk about ion-ion bonds, ionic bonds, right? If you have these ionic bonds, ionic attractions, ionic bonds, you have this situation, right? Yeah. So if I do submerge this in water, this is the negative chlorine, what part of water is going to be attracted to this guy? The hydrogen side, right? Now, one of these is going to start to attract here, right? And then another one might come over and I might have this entire side full of hydrogens pulling on this guy. And that's going to weaken this a little bit. Okay? It's going to pull the chlorine out a little bit, leaving a little space for more water to get into. Now here's the cool thing about water. If I have a hydrogen on this side, I'm going to have an oxygen on this side, right? So, while the hydrogen is being attracted to the chlorine, this hydrogen is being attracted to the positive side of the positive ion. So it can sniggle its way in there, and then it's pulling this chloride out. This may not be the best picture, it may not be big enough, but look at the slides on your own time, you can see it. Essentially what's happening is these oxygens, the oxygen side of water, is going to attack the cations, okay, and pull it off and then surround it. Now here's the thing. Where is ionic bonds on this list? Strong as can be, right? This is the, Dwayne "The Rock" Johnson of bonds, right? Ion dipole forces down here in the Dr. Stobie physical specimen, right? How can ion dipole forces outmatch the ionic bond? Remember what I told you. So when you think about how strong your magnet is, the distance, but then what was the last one I told you they gotta remember from now on?
Size.
Not size. Number, right?
Oh, wait.
I don't care how strong Dwayne The Rock Johnson is. If I had 150 Dr. Stovies, we could probably take them. Right?
Oh, wow.
150, that's a lot, man. I don't care.
I don't know.
I mean, I know that, yeah, but there's 150 of them.
Dude.
Think about it. I mean, maybe 30. You could take 30 of me. I'll even give you 50. 150 though? Oh, what is dog power? Alright. Anyway, but that's what's happening here, right? One ion is being attacked by dozens, if not hundreds, of ion dipole. Different sizes. Depends. Whenever you're talking about chlorine, sure, it's big. And it depends on these polyatomic ions as well. They're big. So,
I thought that would have affected the charge of that chlorine in some way, that it would
affect the charge of it. The charge of the chlorine stays the same.
Yeah, but that was just, it has to do with surface area, right?
We're getting in the weeds. But, the whole point that I'm trying to make here is, even though the ion dipole force is weak, if you have a lot of them, you can overtake these larger forces. Okay? We all good with that? Alright. The other thing you have to think about is, because this is positive and negative, are we ever going to get into a situation where the oxygen happens to get into the chlorine? No, they're going to repel each other, right? Negative chlorine and negative oxygen are going to start repelling each other. So it's kind of like they have little homing beacons to go toward the positive side, right? All right, questions about this? Last intermolecular force. LDF, London dispersion forces. Let me start off by doing another analogy. Let's say I grab all of you guys. We go down to the gym. And I'm like, cool, go, run around, be crazy, dude, just run around the gym as much as you can. Random patterns, just run. Everyone's running around, right? And I'm like, okay, everyone freeze. Snap my fingers, freeze, everyone freezes. Are you guys going to be like evenly distributed across the entire gym? Probably not, right? There's probably going to be most people on one side of the gym or the other, right? I didn't tell you to stick to one side. It just happened, right? That kind of makes sense, right? If I go through and I just, shake up something, it's not going to be evenly distributed. It's going to fall to one side or the other, just random, right? Same thing happens with an atom. Electrons are flying around an atom. You have this, and then every once in a while, guess what? All the electrons just happen to be on one side. Okay? And when that happens, you have this really small, slight negative charge. Before it was upper middle class, this is lower middle class. Okay? This is lower slight negative charge. Just a little bit. Okay? The electrons just happen to be on one side for a little bit. And if that's the case, the other side of the atom is going to have that very slight positive charge. Right? And if there's another atom that's close to it, then this slight positive charge is going to pull on these electrons a little bit, making this side very slightly negative, and this side very slightly positive. And then the next atom here is going to start to pull more electrons this way too. You see how that works? But eventually, these electrons calm down, or they start heading back to the other side. This charge disappears, which makes this charge disappear, and so on and so forth. It's just these tiny little charges that kind of keep the atoms close together. Okay? It's like Velcro. Think about like one hook for Velcro. Very small, small little charge. Okay? If you imagine just one little Velcro hook on the other, you can tear that apart pretty easy, right? So, like that. That is what's going on. So think about something like ethane. Is this polar? Do you see any dipoles going on here? Not really. Nothing, no real electronegative atom here. So we have this guy. Ethane, so you know it's a gas, it's like methane. Has a boiling point of negative 89, right? And so the only real forces are these little London dispersion forces. Kind of keeps things around a little bit. Okay? All good so far? So what's going to happen if instead of this hydrogen, what if I put in an OH? An OH. Now what kind of forces can we have? Hydrogen bonding, right? So what I drew right here, this is no longer ethane, it's now ethanol, or alcohol. What is alcohol's, like, or just alcohol's boiling point? At room temperature, what is alcohol? It's a liquid. We went from a gas to a liquid by doing that. What did we add? Not just an OH, we added hydrogen bonds. Those intermolecular forces are what made this thing go from a gas to a liquid. All good? Cool. All right, let's kind of go in and do this here. So I'm going to go through and kind of make a point here. So methane, the stuff that comes out of the gas that we burn in Bunsen burners, is methane. This, one carbon with hydrogens all around it. Okay. Melting point, negative 164, which means that in order for it to become a liquid, it needs to be negative 164 degrees Celsius. Pretty freaking cold, right? Next one, ethane. I'm not gonna draw the hydrogens anymore because it's just they're hydrogens on the carbon. Okay. If I add one more carbon, negative 88. If I add one more carbon for propane, negative 42. Add one more carbon, butane, negative 0.05, or negative 0.5. One more, pentane, 36. Why is the boiling point going up the longer this guy is? More forces. Which force? Are there dipole forces? Do you see electronegative atoms? No. So, can't be hydrogen bonds, can't be dipole, can't be ion dipole. It is London dispersion forces. Kind of think of it like this. You know, like I said, it was one hook on Velcro. If I have just like a tiny little strip of Velcro, I can pull it off pretty easy, right? Have you ever worn those Velcro suits at the fair and then jump on a Velcro wall? You know what I'm talking about? Yeah. Now, you do that, you slam against the wall. Can you get off the wall? No. You're kind of stuck there until they grab a pole and like poke you down, right? That's how they did it at the fair. But that's what I mean, right? The bigger the thing, the more of those little hooks, the little dipole forces you have. Okay? So the longer the molecule, the more London dispersion forces. Again, what did I say? You know, not only the battery, or not only the magnet or the distance, you also have to now think about number. So each atom, that's a, this makes London dispersion forces. This makes London dispersion. This makes London. This. Everything makes a London dispersion force. Okay, so the bigger the thing, more London dispersion forces. Okay. Actually, if you keep going, so octane, is 8. If you keep going all the way up to, 13 is olive oil, like vegetable oil, okay? That's 13 carbons long. If you go to 23, you start getting belly fat, grease, Crisco, lard. It's still the same thing.
How far can you go?
Oh, there's not infinity, but hundreds. I don't know about thousands. Yeah.
Okay.
How much carbon do you have on the planet?
So, what you mean in nature or like synthetic?
Like, in just saying, how far can you go?
You know what
How
carbon
far
nanotubes
we-
are?
Yeah.
Look into carbon nanotubes. That'll answer your question. Buckyballs. Now, so there's that. The thing is, do you see all of this stuff? Are all of these polar or nonpolar? Nonpolar, right? So nonpolar things are London dispersion forces.
Always?
I mean, that's the only real forces they have.
Alright.
Okay. Are we all good? Make sense? Alright. One other little quick thing is whenever nonpolar dissolving things. So you guys remember the hexane didn't really dissolve the wax very well, right? Water dissolving salt, gone. Here's the thing. Remember what I said before? Water's negatively charged. The oxygen is going to try and find out that positive sodium. Does that happen with nonpolar things?
No.
No. You know how these guys dissolve? It just has to kind of make its way in between things. Just diffuse its way in there. Okay?
So like they repel each other, like they bounce.
Then it's not that they repel each other. It's that they're neutral to each other.
Nothing else.
It has to just make its way there, just kind of like you're wandering around. It would be like this. Instead of going to a dating site to find a date, you decided to just walk around the street until you found someone you wanted to date. What's going to be faster?
Tinder.
I said dating site. All right. All good? Okay. You guys ready for a little organic lesson?
Sure.
Okay. I love organic chemistry. So, here's the thing. Like I said before, this is ethane, right? We all good with that? Ethane. Here's the thing. But, like I said before, I don't want to have to draw out every hydrogen all the time. You get it, right? I also don't want to have to draw the carbons, because in organic chemistry, there's carbons all over the place. So I'm going to redraw this the way an organic chemist would.
So what?
Yeah, the line thing.
So, any point in the line is a carbon, and you assume that it's full up with carbon. Or full up with hydrogen, okay? Unless it's something other than hydrogen. If it's something other than hydrogen, then we'll say what it is. If we don't say it, assume it's hydrogen, okay? So this is ethane, so let's do hexane. 1, 2, 3, 4, 5, 6. Yep. There's hexane. Okay? Because it has 1, 2, 3, 4, 5, 6 carbons, and you assume the rest of it's all hydrogen. Okay? So, of these two, which one's going to have the higher boiling point? A or B? B. Why B? More things? So more what kind of force? More LDFs, right? More London dispersion forces. Okay? So let's play this game real quick. A A or B. I'm going to draw two things. You tell me which one is going to have the, well, which one is more soluble in water. Okay? Which one is more polar? A. Why? That hydrogen bond, though. Whoa! Which one? Top one, why?
Two hydrogen bonds.
Multiple hydrogen bonds, right? Alright, you guys are ready. You ready for this?
What? What? This doesn't sound good.
This is niacin.
No idea what that is.
What does that do?
This is niacin. It's a nutrient. It's actually a precursor to nicotine, but you need niacin in your body to live. So, you know. Nicotine will actually work on the same receptors as these guys to give you a little boost. Yeah, anyway. Niacin, right here. Here's the thing. Do you think that this is going to be water soluble? Will it dissolve in water?
I don't think so.
How many hydrogen bonds do you see? How many places for a dipole-dipole bond do you see? Well, this is in H2, so there's two hydrogens here. So there's two there, one for this nitrogen, one for this oxygen, one for this nitrogen. Yeah. Five different places to connect on for water to latch onto. Guess what? Pretty freaking water soluble, right? So, can you OD on niacin?
I guess. No.
It's water soluble, so think about it. How many different ways of getting water out of your body do you have? A lot. Guess what? It's really freaking hard to OD on niacin. Same thing about vitamin C. So let's let me just pull up vitamin C.
Vitamin C was good for you.
It is, but you can OD on everything. So there's vitamin C.
OD on oxygen.
Guess what about vitamin C?
Yeah, actually.
Do you think it's water soluble?
Very.
Very. You see all of these hydrogen bonds? They're all over the place, right? Vitamin C is so water soluble that literally, if you did nothing but just ingest vitamin C tablets all day, you probably won't OD. Because you'll just start peeing it out.
Oh.
Okay? It may not be good for you, you may not feel good, but you won't die.
Does that mean I can just have a diet of oranges?
I wouldn't suggest it for other reasons, but, you know, I'm not your doctor. Anyway, so we have that. If I gave you this structure, so we all agree, this is pretty polar, right?
Yeah.
And compare it to this, which one's more polar? Vitamin C, right? How many OHs do you see here? Two. What about all this middle bit? Do you see any polar things? All carbon and hydrogen. So this is something you would call fat soluble, okay? Because fats are nonpolar. Nonpolar things dissolve nonpolar things, right? So fat soluble in medicine. There are some medicines that are very fat soluble. They work really well, but they store up in your fat, okay? There are some people who are very overweight. They'll take a medicine because they got sick for one reason or another, right? And then they, later on in life, decide, hey, you know what? I want to get healthy. So they work really hard, they work out, and they drop a whole lot of weight, they burn a lot of fat really quickly, and all of that medicine that was stored up in the fat enters their system at the same time. And then they get really sick and OD on that medicine. It happens. It doesn't happen often. Don't freak out about it. This is like a House case. You guys know House, the TV show House?
Yeah.
This is like a house case, okay? You know. But it can happen. There are a lot of times where your body will store things in your fat, and if you lose weight really quickly, sometimes you feel like utter crap because you just, all the stuff that was stuck, soluble, you know, dissolved in your fat is now in your body, and you got to get it out, you know? It's hard because you can't pee it out because it's not water soluble. So, you have to get it out in other methods. Alright. Do you guys see why we're now getting into the part where we are now talking instead of about, I always say, like pre-chem or pre-AP chem is kind of like learning letters. And so far we kind of starting to get into words. This stuff is when we're starting to get into poetry. Okay? We're now actually taking all the stuff that we learned before and applying it to things. And saying, like how many people here want to go into medicine? Hey, guess what? What did I just talk about? Like medicine and, you know, weird cases, fat soluble, water soluble. You're going to have to remember a lot of these things. You can go through and look at something like estrogen here and go, oh yeah, that's fat soluble. Just by looking at it, right? You can say, like, oh yeah, you got a couple of OHs, but most of this is all nonpolar. So you can get there. Real quick, this guy.
Oh, I've seen those.
So, this is a 3D structure, but it's still the same thing, right? You can kind of see the little squiggles and the little hexes that you see here. Same idea, right?
Yeah,
Don't worry about that.
What are all those pieces?
Now, all the reds are oxygens, blues are nitrogens. So you can kind of go through and go, oh, look at this little pocket here. This little fat pocket here has a whole bunch of oxygens right here. Yeah? So if this is, protein, it does stuff. It has function. If you have a polar molecule, you think it's going to be attracted to this wall? This is where you can start getting into really like grad school level things, like PhD level stuff. And this would be part of a PhD. Look at this structure. Kind of, it's a 3D structure, so we'd have like a program where you could spin it around and go and stuff.
Yeah, what is it?
I don't know what this is. I just looked up a protein. But you can go through and be like, I think this thing is important. So you go through, you change one thing in here to disrupt it. See if it changes the function of the protein. That would be, a good 2 or 3 month long project.
3 months?
Yeah.
How many
You gotta. Well, honestly, what you would do is look at this entire thing, come up with like dozens of different changes you want to do, and kind of do them all at the same time. Okay. Anyways.
What's this squiggly stuff?
Those are alpha helices. The ribbon stuff is beta sheets. You'll learn about that in biochem.
What?
Biochemistry.
Chemistry of the living.
You might actually learn a bit of that in AP Bio.
What's
Anyway, do you guys see?
biochemistry and
Electric
So let me ask you guys this.
chemistry is a different molecule. Biochemistry is chemistry like the living environment.
Let me ask you this. If I gave you something like this, and I asked you to make this more water soluble, could you do it? Just by drawing it. They didn't have to actually come up with an experiment. What would you do to draw? What would you draw on here to make it more water soluble?
more oxygen.
More oxygens, right? More nitrogens, more electronegative things, right?
It would be more oxygen points, right?
It could basically just change the estrogen.
So looking at this guy, rank these guys from most to least water soluble. Which is the most water soluble out of these? Bottom right. What's the next?
Bottom left.
Then?
Top right. Question, why is there a double, what's up with the double bond?
The double bond? Well, can this thing make a hydrogen bond?
No, I don't think, no, it doesn't.
Doesn't have a hydrogen. Can it still do dipole? Dipole.
Yeah.
So, which one's stronger? Hydrogen or dipole? Dipole. So, or no, hydrogen. So, this one, then this one.
Okay, so
Atoms on a roll.
Okay. So, if I gave you a structure like this, could you go through and explain why?
Yeah.
yeah.
Fairly confident.
Very good.
Unless you put something else, it's not hydrogen bonds.
Good. Because I think for the tomorrow we're going to go through and basically just be like, I want you to do that before every single one of these. I want you to draw a picture and give an explanation for all of them.
Are we gonna do metallic one?
We're not gonna do that.
It's a
We're not going to worry about it. I'm not a physical physicist. I'm more of I'm very much a biochemist. I am a biochemist.
Biochemistry and molecular chemistry.
Molecular biology, it's kind of like looking at the same thing from two different places. So a biochemist would be more interested in the chemistry of this, like what is the bond angle, what is the bond energies, those type of things. A molecular biologist would be like, what's the function of this thing? Those are two different questions, right?
So, molecular biologist.
Are we doing anything important in academic team?
Today,
Yeah.
I mean practice,
Alright.
but I mean, and if you got stuff to do, you got stuff to do. I'm not gonna yell at you for not being an academic